Alright, hello everyone, I'm Stefanos Baziotis. I'm a fourth year PhD student at UIUC working at the intersection of programming languages and databases. And this is a presentation I gave at the compiler meetup at UIUC a couple of weeks ago. And I think it's useful enough that I decided to record it. So here we go. Now let me remove myself from the frame because I'm going to be taking a big part of the screen. Okay, let's get started. By the way, this is the original title of the presentation. I didn't use that for the YouTube title, but I feel like why not include it in the slides? So let's talk first about SQL. Now, actually, we're not going to be talking much about SQL during the rest of the presentation. We're mostly going to be talking about query plans, which is what SQL is translated to in basically every query engine out there. That said, most people are familiar with SQL, so we're gonna start from a reminder to that, and then we're gonna see how to translate SQL to query plans, and then we're gonna be working with query plans. This is a very simple SQL query. We just have this table with these 3 columns and 2 rows. I just select 2 of the columns, and this is called a projection. I project some of the columns, and so the result I get is this. You can similarly imagine like filters when you have, say, a where clause in your SQL query. I think this is very easy to see how it works. I do, though, want to take a minute and talk about joins because we should be sure we're on the same page. I now have 2 tables and I've colored the rows. You'll see shortly why. And here's a very simple join. I select the name, age, and price from customers, and I join customers name with orders name. Really, this name, age, and price should have been like customer's name, customer's age, orders price, or whatever, but who cares? The way to think about a join is, well, you can think of it as a 2-step procedure where first you think of a Cartesian product. It's like take every row from the one table and then every row from the other table and just yield their concatenation. This is what we get out of that. This is why I've colored the rows of the original tables, because here you can see every row being matched, every row of one table being matched with every row of the other table. You may want to pause the video at this point and just make sure that this Cartesian product makes sense. Now, a join is a little more than a Cartesian product because it has a condition. I'm only going to keep the rows where something matches in the rows of the 2 tables, which in code we can express with an if. We go back to this visual representation. We just concentrate on this C name and O name columns, and we only keep the rows where these columns are equal. So we have this row, and this row. So this join is going to return 3 rows. Now, of course, this implementation we see here is kind of a reference implementation. It's incredibly slow in practice. It's O1 squared. Most of the implementations use some other method like hash join, which is what we're going to see, where basically you store the rows of one table into a hash table, and then you look up the rows of the other table for only those that match. Now let's talk about query plans, which, as I said, is what SQL queries get translated to. Now, query plan is a tree of relational operators, and you have edges from children to parents. The benefit is that we have explicit flow of data and order of operations, as we'll see in a moment. So we're going to start with a very simple query plan. Generally speaking, for the rest of this presentation, I'm going to have the SQL query on top and then the query plan on the bottom. For the rest of the presentation, we're mostly going to be talking about the query plan. But of course, you can always take a look at the original SQL query if you are unsure. Now, here's a query plan that has 2 operators. It has a name table, which is basically just a scan, meaning it's just an operator that gives you all the rows of a table. And then we have a project operator, which is usually denoted by this pi, which essentially gets as parameters the columns that we need to keep. Here's a slightly more complicated query. We just have a filter into the pipeline. So here we have data flowing from customers, so basically all the rows, and then we have a filter, a selection on a condition, and only the rows that pass the selection go into the projection. Now, one thing to notice already is that a query plan, as I said, makes explicit the order of operations in a way that SQL doesn't. For example, already by looking at the SQL query, you can maybe think like, does the project happen first or the filtering? And a query plan makes that very explicit, and so it's much more interpretable. Here's a slightly more complicated query. This is basically the most complicated query we're going to see in the presentation, or no, actually almost. We have a join on two tables, and a join is the only operator we have that is going to have two children. And we, as I said, we just take these two operators, scan the rows, they send them through the join, and then they go to the selection. Another thing to notice is that the arrows denote the data flow, meaning how data flows from one operator to the other. Okay, this is actually the most complicated query we're going to see in the presentation. If you take a look at the SQL query, it's actually very hard to read, at least for me. But if you take a look at the query plan, it's extremely easy to see what's happening. You have data flowing from customers through a filter, and then data flowing from orders through a filter, and then this both filtered data go through the join operator. So, as I said before, we have a tree of relational operators. So the nodes are relational operators, and edges go from children to parents, and the benefit is explicit flow of data in order of operations. A query plan, generally speaking, is an abstract specification of what needs to happen. It just tells us, for example, data, like all the rows are going to flow from here to here, and then only the rows that pass the filter are going to make it, blah, 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 right? But it actually doesn't really tell us how the execution happens. So for example, does data flow one tuple at a time? Oh, by the way, probably I'm going to be using a lot the word tuple. A tuple is just, well, really you can think of it as a row, but usually a tuple is a more generic term which encompasses really subsets of rows. So for example, so what you return here is tuples that only have the name and age. So the original rows have name, age, salary, but we only return tuples that have name and age. So does data flow one tuple at a time? That's one question. The other question is, how is the data flow triggered? Meaning, what is a control flow? Meaning, who calls who? So these characteristics are specified by what is called a processing model. And the simplest and yet most used processing model is the Iterator/Volcano model. In this model, every operator implements a next function. Each operator gets tuples one at a time from its children by calling their next function. And execution starts at the root. So let's start visualizing that. Now, we're going to have two types of arrows. We're going to have control flow arrows, which are going to be horizontal, and they're going to be showing us where we are at any point in the execution of a program, kind of like a debugger that steps through the program. The data flow arrows are going to be vertical, or generally upwards, moving, because some of them are going to be slanted. And they show us the flow or direction of data. Here's a very simple implementation of the operators in the Volcano model. So the projection operator just says, I want to get the tuples from my child's next, and it emits the projection of this tuple, obviously based on the parameters here. A scan is a very simple implementation. Obviously, it just loops through the tuples of a table and just emits them. Now, let's see how this works. As I said, execution starts at the root of the tree, so it starts, in this case, in this projection operator. And so, of course, the first thing we do is we go here and we call our child's next to get the first tuple. Now that blocks, meaning at this point we're just waiting. So we go here and we just get the first tuple and we emit it. The data goes back. We go again back to the projection. We emit now the projected tuple and we call again our child's next. That blocks again. We go to the child and so on and so forth. The thing to notice here is that basically the operators retain state, meaning the second time we call this scan, it's going to return us the second tuple from customers. It's not going to start from the beginning. So it's kind of like the yield kind of style that you have in Python. This is a slightly more complicated query. Here things get more interesting. So we go to the root again, we call our child's next, that blocks. We go to the selection. This calls its child's next, which also blocks, and now we go to the child, that returns the tuple. Assuming that the tuple passes the predicate, we emit that back to the projection finally just projects the tuple. Now there's this term, it's called a pipeline, well, this term is actually used a lot in the literature. And to be honest, I'm not exactly sure that there's any kind of agreement on what exactly a pipeline is. So here's what a pipeline is for this presentation. A pipeline is a subset of the tree that doesn't wait for all data from a child, and so essentially just passes data around without materializing or copying. So, well, before we go to the join, here's what I mean. Let's say we are in the projection and we want to get a tuple from the selection. Once we get the first tuple from the selection, we can immediately emit it. We don't need to wait for the selection to give us all its tuples. A better example may be when the selection calls the scan. So the selection just calls the customers table for the next tuple. And if it passes the predicate, it just immediately emits it. You could imagine a very stupid way of implementing this thing where the customers operator just gathers all the rows and sends them as a packet to the selection operator, right? But this is generally not great because we're allocating big amounts of memory, and we don't need to do that because, again, we just can't keep emitting as soon as we have a tuple coming from one of the children. Now, what is a pipeline splitter? Is a join. Because in a join, we need to get all the data from the left child before we can start emitting any data. And the reason for that is because to see if there's a match from the tuple coming from the right child, we need to have consumed all the data in the left child. So let's see how the implementation of a join operator works. So this is a simple hash join where you take all the tuples from the left child, you build a hash table with them, and then for every tuple in the right child, you probe the hash table, meaning you look up the tuple from the right child and you emit their concatenation if they match. As I said, to know if you have a match from any tuple coming from the right child, you have to have consumed everything from the left child. You can't just consume one thing and then say, okay, let me get the right tuple and see if they match, because maybe your right tuple matches, but it's from a left tuple that is further down the line. So this needs to block completely until all the data from the left child is processed. So a join splits our query plan into two pipelines. The first pipeline is this one, which is the left child. And again, this is a pipeline because we can just keep emitting data as soon as a tuple arrives at the selection. If it passes, of course, the predicate, we just emit it immediately. But then we block here, right? The data can't just keep passing through. Once we have consumed all the data from this one pipeline, we can just start emitting data immediately from the right pipeline. For example, as soon as we have a tuple from our right child that matches something in the hash table, we immediately emit it. This concept of pipeline splitting is going to be important later on when we consider code generation schemes. This is a note on terminology. The Iterator/Volcano model is usually called an interpretation-based execution model, which to me, as a compiler expert, or a compiler researcher, whatever. So let me try to clarify that. So interpretation has nothing to do with whether we're using an interpreted language. Okay, let's just start from that. You can assume everything is in C++. If you're thinking of interpretation of any language, that should be the query plans. But really what interpretation means is that every operator is independent, and executing a query plan is a composition of independent operators. So if we try to get a little bit more practical, you can imagine that like every operator is potentially in a different translation unit or in a different module, depending on however you want to think about it. They're compiled differently or whatever. And so the code of an operator doesn't differ across plans. There's no code specialization according to the particular plan that we're trying to execute. In other words, no matter which plan we have, we're just going to compose the operators to finally execute the plan, but the implementations of the operators don't change. You can think of the operators in this case as basically reusable components, as building blocks. You can use them to build up a plan, but the building blocks don't change. The benefit is that an operator can be modified, thought of, and debugged independently. So for example, if we go back to one of to say this plan right here, and I'm having some problems, I'm not really sure what's happening, And I think the problem is in the selection. Well, I can just go and see the code of the selection independently, debug it, whatever, add prints into it, and read the code independently of the code of any other operator. Again, this can be thought as different modules compiled independently. Another view, perhaps not a very accurate one, but it may offer some kind of intuition, is that each operator is a bytecode and a plan is executed one bytecode at a time. So similarly to, say, a language like Java or JavaScript, the bytecodes are the building blocks that you use to compose the program that you want to produce, but the bytecodes obviously are independent of each other, and the execution of a bytecode is independent of the execution of any other bytecode. So for example, you can go to Python and see the implementation of the add bytecode. Just observe the code of that particular bytecode. Now that, however, has a drawback. The drawback is that there's no inter-operator optimization. Like for example, if an operator calls another operator and there's some way to optimize this whole piece of code, you don't do that because they're just completely independent. So the summary of query plans and query interpretation is that every operator is independent. Executing a query plan is a composition of independent operators. The code of an operator doesn't differ across plans. And the main benefit is that they can be modified, thought of, and debugged independently. A small interjection here to talk about vectorized interpretation, which sounds fancy, but basically it's a Volcano model, except multiple tuples are flowing at a time. That on its own is not super fancy, but the benefit comes from the fact that we use SIMD, which is single instruction multiple data, to process multiple tuples at a time. So here's a simple case where we have a serial implementation of the selection, and here's a vectorized implementation. We can imagine this thing is vectorizable. P is broadcast to a mask, and then accordingly we return some of these. Now we're going to go to something that is a little bit unfortunately hard to understand in the literature, at least it was for me. And honestly, the main reason I'm giving this presentation is to clarify this part. So the core idea of code generation or query compilation, which is another way of executing query plans, is to accumulate all the code for a query plan into a single piece of code and then compile this whole piece. The benefits of that is that, well, first of all, it removes overheads. It removes the overheads of, for example, one operator calling another. Again, as I said, you can think of them as being in different functions and different modules. A function is calling another function that has some overhead. You can inline that, for example. Also, there's cross-operator compiler optimization. So now you have the code of both the operators. The compiler can just choose to do whatever it needs to do to optimize this. Because essentially, you can think of a parallel with link time optimization, where now you have a view of all these independent modules. And also, the code now is specialized to each plan. You're composing, you take a plan, and for this particular plan, you compile a specialized version just for this particular plan. It's not anymore a composition of independent operators. Let's start with a plausibility statement, where I'm going to try to first motivate that, well, it should be possible to gather all this code for, say, a simple query plan like this into a single piece of code. I mean, each operator just pushes data to the next operator. It should be possible to fuse everything into a single loop. It should be possible to write this into that. Because think about it, do I really need 3 loops that are going through tuples? No, because really I just have tuples coming from this customers thing. There's no need for this loop and this loop. So for example, I can just say, okay, just loop through all the tuples in customers. If a tuple passes the predicate, just emit the projection of that tuple. So this is kind of our goal. This is where we want to get at, and hopefully the benefits should already be obvious. Like now we just have much less overheads. We don't have all this child next calls and all this monstrosity, right, that looks kind of terrible from a performance standpoint. The idea of how we're going to do that is that we're basically going to have a code generation scheme where if I see a scan operator, emit a loop over the tuples of the table. And then if you see a selection, just emit an if. And then if you see a projection, put a projection function, and somewhere at the end, put an emit. Obviously, this is just very vague right now, but we're going to get very specific, trust me. I'm just trying to show you the high-level idea. So here's where we get specific. So I'm going to talk about a code generation scheme. Now, this code generation scheme is inspired by this paper efficiently compiling efficient query plans for modern hardware. Sorry, I just realized this double use of efficient, that is a bit funny. Now, here's the problem. The code generation scheme that they have in the paper doesn't really work, for me at least. I tried to apply it in practice. Let's just follow the code generation scheme for some simple query plans, and the code I was getting was a little bit bogus. Now, I may be wrong, so you may want to take a look at that paper, but I'm going to show you a code generation scheme that I came up with that is inspired by this paper, which, as far as I can tell, actually works, and we're going to see it rolling in practice. The first thing we're going to do is that every plan has a special emit node at the top. That's just a very minor addition. Just take a query plan as it is, you stick an emit node at the top. Here's now what we're going to do. We're going to use these two functions for every operator. They are called produce and consume. Produce just recurses down the tree, and consume goes up the tree, generating code. Why they're called produce and consume? Well, because that's how they call them in this paper that I mentioned. And so hopefully, by using the names produce and consume, if you want to go and look at the paper and try to draw parallels between what I'm doing and what they're doing, you can just have an easier time. At the same time, quite inconveniently, produce and consume are not particularly great names for what these functions actually do. But this is what we have to live with. So here's the code generation scheme. It looks scary, but trust me, it's not that scary. All right. So first here I have some just simple functions that are used to produce nicer code. Or well, if you're outputting Python and our code is going to be kind of Python-like, sorry about that. This is necessary actually to make sure you're using correct annotation. Now, we first of all have the produce functions. The produce functions for every operator except the scan are just super boring. They just call their child's produce. So the emit node, which is the topmost node, calls it child's produce, with same for projection, same for filter. Now, where things get interesting is in this scan produce thing, because this starts actually generating some code. And in particular, it generates the for loop that we just said. We're going to return to that, don't worry about it. The important thing to note is that the scan produce doesn't call its child's produce because scans don't have children. Now, the consumes are where code generation happens. Now, I don't actually think it makes much sense to take a look at the code of these functions and start explaining them in the abstract. Let's see this thing rolling in practice. Okay, so this is me really trying to fit everything into a single frame. So here's how this is going to work. On the left and the right, you have the code for the code generation scheme, basically. In the middle, we have the query plan that we're going to try to compile. And on the top, in this, what is it? Is that beige? Is that orange? I don't know. In this box, anyway, it's going to be the code that we output. Things start at the top, and we call the emit produce thing. That's the only thing that we just have to do to get this thing rolling. So that, as we said, calls its child's produce, which calls its child's produce, which calls the scan. The scan is where interesting things happen. So we first do indent, which in this case is nothing because that starts at 0. And we just pick a new variable name, which is basically going to be the variable name we're going to use for the target of the for loop. And then we increase the indentation, and inside the for loop, we set this variable car tuple. Now we set this variable to whatever, to this target that we picked earlier. Now, kind of the invariant of the whole code that we're going to be generating is that car tuple at any point in time has the tuple that this loop is supposed to emit. Now, as operators get added, or the code of operators gets added, this value may change, but in the end, car tuple should have the tuple we want to emit. Okay, so now we execute our parents consume. So now we go to the filter consume, and what that does is similar to the high-level description that I had earlier. Well, you know, what should a filter do? It should generate an if. And the if is just basically pretty simple. I just take the condition, whatever that is, and the condition is on card tuple. And you see why this invariant is pretty important, because for example, at any point in time, I want to say, well, I want a condition on the current tuple that I'm about to emit. What is it? It's going to be in this variable. So that's what we print. We increase the indentation again because we're going to shove stuff, like whatever happens in our parents, it should be inside the body of the if. And again, the intuition here is that, well, any code that the parents, our parents like this projection and emit generate, should be code that works only on the card tuple that is actually passing the condition. So one way to think about it is that as we go from bottom to top in the query plan, in the code, we increase the nesting depth, which again makes sense because you're only going to project whatever has passed the filter, and you're only going to filter whatever has come from customers. Okay, so we call our parents consume. Now this is actually pretty simple. It just sets card tuple to the projection of card tuple, and it finally calls its parents consume, and its parents consume just emits the card tuple. So that's it. Basically, you've seen all the basic ideas that go into this code generation scheme, right? So the environment is card tuple, at any point in time has the tuple that we want to emit. And so for example, you see here that the projection modifies the card tuple, but the emit doesn't have to know whatever has happened to card tuple. It only needs to know that the tuple that it needs to emit is in this variable. Now, it should be relatively obvious, hopefully, that this code generation scheme works for any kind of plan that has projections and selections and scans. So for example, here's a query plan that has selection, a projection, a selection, a projection, and it also has a scan on the bottom, and the emit we stick on the top. So I'm speeding up here. We have gone all the way down the tree through the produce. Yeah, the produce calls, and now we start going up with consumes to generate code. So we generate the for, now we generate an if, we generate a project, we generate an if, we generate a project, and finally we generate the emit. So maybe you want to stare at this for a little bit and just be sure that it's making sense that this if should be inside this if, because this if works on whatever is coming from this if. Now, we need to talk about joins. This is where things get slightly more interesting. This is going to be based on a hash join implementation, which is what we saw earlier. The code I have here is basically kind of the same. I've just removed a lot of unnecessary code because, again, I'm really trying to fit everything into the screen. So I've removed all the indentation code, well, the indentation functions, and I've also removed all the produces that just call their child's produce. So we're left with most consumes, the scan produce, and now we have the join produce and the join consume. The join produce is very simple. It first calls its left produce and then the right produce. The join consume is where things happen. Here, again, you see me failing, trying to fit everything into the screen. So now I have the query plan in the middle, the code for the code generation scheme on the left and right, and the output code is going to be on the bottom left. Now let's start executing this thing. I'm splitting things up a little. We just get into the join produce by calling the emit produce, which calls its child's produce, which calls the join produce. This then calls the left produce. This goes all the way down to call the scan produce. The scan produce produces or prints the loop, and it sets card tuple, and it calls its parents consume. So now we go to the filter consume, which generates the if, and that now calls the join consume. Now the join consume, as I said, is the most interesting piece. The join consume does different things depending on whether we're coming from the left child or whether we're coming from the right child. And so that's actually why all this consume calls, they get this caller. They need to know where they were called from. So if the caller is the left child, then what we do is we just build the hash table with the card tuple. And what we do is we reset the indentation. And the reason is because we're done generating this loop. And in particular, this is the concept of the pipeline splitting. So remember, we have these two pipelines here. And the reason this code generation scheme works like that is because this loop needs to finish completely before we can start executing the loop for the right pipeline. And that of course, in code is highlighted by the fact that we reset the indentation. And then this function just returns. And this goes all the way back to calling the write produce. Why? Because this returns, so it goes back to this consume, which goes back to this produce, which goes back to this produce, which goes back to this. We were here and this kind of thing happened. So now we call the write produce, and the write produce mostly does the same things. I mean, we generate the second loop that goes through orders, we generate the if, and now we go to the join consume, but now we're coming from the write child. What we generate is we first probe the hash table and we generate an if, right? So if the probe succeeded, then we say that the current tuple is the concatenation of these two. And that is basically it. It calls all the way up the consumes, and you can see that finally we generate the projection and the emit. And also, again, observe that the emit is all the way into the ifs, right? So we're not going to emit something unless it passes all these ifs. And again, this whole pipeline is put into one single big loop. Just a side note, if you're familiar with multi-stage programming, this is basically one case of it, right? Because we run the program, but running the program really gives us another program that we will then compile again. Now, coming back to query compilation and code generation, the benefits are that it removes overheads, cross-operator compiler optimization, and specialized to each plan, as we just saw, right? The code that you see here is for this specific plan, but it has some drawbacks, right? Everything is smushed together into a single piece of code. It's very hard to understand and debug. You can't go and say, oh, I want to see what's happening in the joins. Well, no, because the joins are like some around the code along with code for the filters and the projections and things like that. And in particular, things get even worse because many times this code generators, instead of generating, say, C++, they generate LVMIR. The final thing I would like to talk about is about this Sigma 2024 paper that I think is pretty nice. It's called Query Compilation Without Regrets. Essentially, this paper tries to get the best of both worlds, meaning query compilation and query interpretation. So it wants to retain the independence and debuggability and the ability to think of operators independently that query interpretation gives you, but at the same time, they want to get the performance that you get from code generation. At this point, I think it would be a good exercise to pause and ponder about the core idea, like how you could reconcile these two ideas. Okay, so if you're back, core idea they use is tracing. Tracing is something that became popular from JavaScript engines because, well, JavaScript engines face a similar problem. There was this very famous paper, unfortunately I'm forgetting the name of the paper, but basically it's the paper that introduced TraceMonkey. So let's talk a little bit about tracing. The idea of tracing is that let's say you have some code, you create traces of the paths that the code may follow. So let's say you go to path 1, which is, let's say, the common before the if, then you get to the then, and then the common after. And then you have trace 2, the else code, and the common after. Basically, the idea of tracing is that you generate these traces and then you compile them to machine code, to optimize machine code. So this code on the left is usually some kind of interpreted language like, well, not JavaScript, but JavaScript bytecode, let's say SpiderMonkey bytecode. And then the idea is that you generate for some hot paths some optimized machine code to execute anytime you see this path in the future. Now, to see this a little bit more in practice, like how that could work, this on the left is some simplified a little bit, the SpiderMonkey bytecode. It just looks horrible, unfortunately, because it's what people call a stack machine, where you think of a value stack that the program has, and then the code works by pushing and popping things from the stacks. So we push A, we push I, we push B, and we push I, and then this getElem is first going to get BI, because it's going to pop two things from the stack, and the top two things are these. Then we're gonna push C and I, so this is this also is going now to get the element ci, meaning these two getElem are lookups. And every time they look up an element, they put it back into the stack. So if you think about it, the stack after the first getElem has the value of bi, the second getElem pushes the value of ci, and add now pops two elements, which is the bi and ci, adds them up and puts it into the stack. And now setElem needs three arguments. It needs the pointer, it needs the index, and it needs the value. These were in the stack from the beginning, and we now on the top we also have the result of the add. Now in a normal scenario, we just interpret the code. But to compile, meaning to generate traces, you replace the implementation of each operator such that instead of executing the code, it emits IR. Let's say for simplicity, LVMIR. Now, to emit LVMIR, you need to know the types. But this is something that you know at runtime. And this is why tracing is a dynamic technique. There's no point trying to, for example, to say, okay, I'm going to take this code and I'm going to create a trace for it statically, because you really have no information about the types. So if you try to generate code, really the code is going to be as performant as this, even if technically it's an LVMIR. So the performance comes from from knowing, for example, that I is an integer and A is a pointer to an integer or pointer to a float. Then for this getElem, for example, you can get this very specific code. Now, instead of executing the program, you just run the program, or quote unquote, running the program just generates code. And then you compile this code to machine code that you then execute whenever you encounter this trace. Now, here's how Nautilus, I believe is pronounced, here's how it applies these ideas. This is kind of an extrapolation on my part, because unfortunately many details are omitted in the paper, so I had to do some guesswork. With this disclaimer, let's see how it works. The idea of Nautilus is that it gives you a single unified interface where you can implement your operators, thinking of them independently, meaning as you would do in an interpretation engine. So these are the operator implementations that we wrote, and these are the operator implementations in Nautilus, as far as I can tell. You can see that it's actually very nice. They look very similar to the pseudocode that we have written. So for example, here you just execute the projection on the tuple you get. The selection is just the expression, in this case, the condition. So if our tuple passes the condition, then we execute on this tuple. And of course, a scan is just a scan. It just loops through tuples. Now, as I said, Nautilus tries to bridge code generation and interpretation. The way this works is, of course, you have an interpretation mode where these operators are executed independently the way we saw. But if you want to get code generation, it wants to trace your program. So we first want to quote unquote execute the program, but instead of actually executing the program, we want to be generating code. This is simple for, say, something like this, because in this case, we just emit a projection, the projection code, by calling this function. But things get tricky when you have structures of the host program language you don't have access to when you're executing the program. So here we have an expression like a condition, right? So expression is of some class, let's say condition, and you have defined this execute method such that if I'm in the interpretation mode, then I'm just going to, whatever, execute, check the condition. But if I'm in the code generation mode, I just want to generate code for the condition. So let's say you're generating code that looks like this. But the tricky part is, how do you generate the if, right? Because you don't have control over the if. In other words, ideally, what you would like to do, or what Nautilus would like to do, is to go and overload if and say, if I'm in interpretation mode, then just execute the if as you would do in a normal C++ program. But if I'm in the code generation mode, I want you to, instead of executing the if, to generate an if, meaning generate a conditional jump or something like that, a conditional branch in LVMIR. But of course, C++ or C++ compilers, they don't give you control over that. You can't just overload built-in features of C++ like the if. So what's the idea? The idea, and again, this is extrapolation on my part, comes from this paper that they cite, which is called buildit. Now what buildit does, that it overloads the cast operator to bool of this expression, which is pretty fancy. And if you overload that, then whenever you execute that, you know that you're part of some kind of condition. If my cast operator to bool is executed, then if I'm in code generation mode, I'm basically going to return none or whatever. It doesn't really matter what you return, because the if is actually going to be executed, right? Again, as I said, you can't overload that. The if is going to happen. So you can say you're going to return true or who knows what. But the important thing is that now you know you're inside an if. So instead of just generating this, you're also going to generate a conditional jump. Of course, there's a further problem that we need to deal with, which is that there's some code that needs to be generated if I get into the if, and there's some code that I need to generate when my condition is false. So for example, I want to say here, okay, whenever the condition is false, I want to go ahead and generate this, the then part of the conditional branch. But if it's false, then I want to say generate no code or return back or whatever. And to do that, they execute the pipeline, the plan, repeatedly until all paths are visited. Now, how is tracing different than code generation? Well, this is a realistic code that they have from the paper. The way it's different is that you have a single unified interface. So the DB implementer deals with one piece of code. They can debug it very easily when they do interpretation, but very easily folks can deal with stuff when they're doing code generation. Okay, so these are the takeaways of this presentation. Interpretation, we execute each operator independently. Compilation is code gen from a plan, a single piece of code, and then compile that. And then Nautilus, write one implementation of operators. You execute this normally during interpretation, but you trace it if you want to do compilation. So that's all I had for this presentation. Please let me know if anything was unclear, and I'll try to clarify that down in the comments of the video. And thanks a lot for watching. I hope this was useful.